Okay, so let me see if I can explain this to find the Jordan form of a matrix. The matrix I'm finding the Jordan form of is from the book. Don't remember which exercise. But here's the first row, 7, 1, 2, 2. Second row, 1, 4, minus 1, minus 1. Third row, minus 2, 1, 5, minus 1. Fourth row, 1, 1, 2, 8. Now, notice what I've done here is I've subtracted z. And I'm using SymPy for this because I don't actually know how to do it any other way. To find the characteristic polynomial, I take the determinant of m minus zi, and SymPy allows me to do that symbolically. So here I do take the determinant, and then I get the characteristic polynomial. Okay, so I wonder if I can just execute this much. Let's see if this works. Okay, let's see if that works. So the characteristic polynomial, I hit Control Enter. I guess it doesn't work. It executed everything. So characteristic polynomial is this here. C to the fourth minus 20. This doesn't tell me very much. So I need to find the roots. Let's go on and find the roots. Actually, let me make this bigger. It looks too small. Okay, so let's see. There should be a way just to run the selection. Let me see if I can do this. So if you look at SymPy, SymPy has some documentation. I don't remember exactly where I found it. I think it's here. So it gives the basic methods. Yeah, these are very important for the basic methods. Yeah. And so I just basically use this stuff. The nice thing about SymPy is it also does REF, which NumPy doesn't do for some reason. All right, so I've got the roots. Let's see if I can run just the run selection. There we go. Okay. All right, now, turns out that all the roots were 6. Is that what it says? Yes, all the roots are 6. Okay, so we know that it has at least one eigenvector with eigenvalue 6. So let's find the null space. The null space will be the set of eigenvectors, right? Okay. So let's go ahead and do that. I think I can just run these 3 because I already ran the other one. Run selection, Control Shift Enter. Let's see what it says. All right, here's the null space. 2 eigenvectors. So the null space is 2-dimensional. All right, so you've got 2 strings. All right, so you've got to trace it back even more. So let's look at the null space of the next of the square. Right here, I squared it, and I'm taking the null space. I think it's Control Shift Enter. Okay. So let's see. What does it say now? All right. So this is the null space of the square. Actually, I should do both of them because I want to compare them. Right now, the null space of the square should include the null space of the matrix itself, because if m minus 6i times v equals 0, then certainly m minus 6i squared times v is also 0. Right. So let's see. All right, so we've got I printed out everything. Here's the null space of m minus 6i. That's this part here, this vector and this vector. Here's the null space of m minus 6i squared. I have the first basis vector, then I have this vector, and then I have this vector. All right, so what happened? So I increased my dimension of null space by 1. That means that one of the strings must have terminated, because I've only increased it by 1. All right, so I have one string of length 1, and the other string must be of length 3 because it's 4 by 4. All right, and you can verify that when I take the null space of m minus 6i cubed, then it turns out that everything is in the null space. You can see the first basis vector, second basis vector, third basis vector, fourth basis vector. All right. So how am I going to trace this back? So my two strings are clear. I have one string of length 3 and one string of length 1. All right, let's see. So how are we going to find these strings? Because the string is going to end in one eigenvector, but I don't know which eigenvector it ends in. So what I should do is take something that's in the null space of m minus 6i cubed that's not in the null space of m minus 6i squared, and then hit it with m 3 times. And that's going to be part of that string, because there's no other way it can be, because the eigenvector, the singleton eigenvector, has no vector that goes to it. It just goes to itself. All right. So when I look at the null space of m minus 6i squared, you could write these three down. All you would have to do is find some vector that's not in the null space of m minus 6i squared. So it's not in the span of these. And when I looked at this, I saw, well, this vector has, I figured out that 0, 0, 0, 1 was not in the span because this is the only one that has, this is the only one that has a 1 of these three vectors. This is the only one that has a 1 here. So we'd have to have 1 times this. Then we have a minus 1 in this place, which means that this would have to be a plus 1, but it doesn't cancel this one. So I figured out that 0, 0, 0, 1 is not in the null space of m minus 6i squared. So it must be in the null space of m minus 6i cubed, because the null space of m minus 6i cubed is the entire space. All right. So this one here was, so this is pick a vector that is not in the null space of m minus 6i. Okay, and I found out that this was it. Okay, and then here, print the string. Okay, and let's see what we got. So if we print this one, I think I'll have to do this here. I'll just execute these here and print just this selection. All right, so what happens, it went to 2 minus 1 minus 1, 2, 3, 3 minus 6, 3, and then it went to 0, 0, 0, 0. Okay, so this must be my eigenvector right here. That's one of my eigenvectors. All right, so now for the other eigenvector, I can just choose any of the two eigenvectors, original eigenvectors I found, that's linearly independent of this. Okay? And that will give me two linearly independent eigenvectors that will span the null space of m minus 2i, m minus 6i rather. Okay. So what I did, I took this vector. This vector is the beginning of the string. Then this vector goes, as the first vector it goes to in the string is this vector here. Next vector in the string it goes to is this vector here. Next one is this vector here. Because this is the null space. So and then let's see, and then the last one. So I'm sorry. This was one of the other eigenvectors. So let me start again. This was the vector. This was its image in the string. This is actually an eigenvector here. There's a third vector in the string that is mapped to from back, and then this is another eigenvector. So that's what we've got. We have this vector passes to this vector, passes to this vector, passes to 0, and then this is the other eigenvector. Okay. Now it will give me a basis P. Now when my matrix acts on this matrix, it will have the Jordan form. Okay, so let's just look at this matrix. This matrix doesn't really show you anything the way it looks, but I'm going to use this matrix as a change of basis. Whoops, I think I made a mistake. Okay, I'm going to use this matrix as a change of basis matrix. Sorry, it's messing me up. I don't know why it won't let me do this. Okay, so Control Shift Enter should just give me P. Yeah, there's P. So it doesn't look like much of anything. right? So, but now what I want to do is I need to transform the vector M using this as my change of basis matrix, because with respect to the basis P, my matrix should look like it's in Jordan form. Okay, so here what I did was I took my M up here, which I used to get the eigenvalues, and I just put z equals 0. That gives me my original matrix M. Okay, and then I applied the change of basis matrix to that. I applied this P to that. P inverse times M times P. And you'll see magic, what happens. Sorry, it's not helping me. Okay, Control Shift Enter, and we'll see what happens. After I apply M, here you go. You've got 60. The first row is 60000. Second row 1600. So you can see that first part of the block there. Then 0160. Okay, so that's a 3 by 3 Jordan block right there. And then this is the last eigenvector. All right, so that's how that works out.